So this lecture covers the first part of Chapter 10, Sinusoidal Steady State Analysis. You're going to find that there's actually nothing really new in this chapter. You're going to be applying all of the things you've already learned, but everything is just going to be using complex numbers instead. So to analyze these AC circuits, first keep in mind that we are in the steady state. That means that we're not looking at the transient analysis at all. We're not looking at a DC voltage turning off or turning on. We are looking at a circuit that has an AC signal applied to it, and the AC signal has been applied to it for a long time, so that it's in a steady state. So the general process, this is right here is what your book says, but the general process says transform the circuit into phasor or frequency domain. Solve the problem using circuit techniques, and these are all the techniques that we've already learned. And then transform the resulting phasor back into the time domain. So I reworded it a little bit down below. Basically, you go to the circuit and you replace all of the components with either their reactance or their impedance. Actually, it's probably going to be their reactance, which is a complex number expressed in ohms. So for example, a capacitor, its reactance, usually given the symbol X sub C, is 1 over j omega Fc, which is minus j over omega Fc. So this is a complex number. Not complex, this is an imaginary number. And so on your schematic, just replace the value of C, or right beside the value of C, write its reactance. Same thing with an inductor, and a resistor is still a resistor. And do recall that the frequency of the circuit, frequency in hertz, is related to frequency in radians per second by omega equals 2 pi f. And then after you put all of the ohms basically on the circuit, so you've computed all of the ohms, which is specific to a particular frequency that the circuit is running at, then you just solve the circuit using techniques that you already know, except that all of your numbers are now going to be complex. And then when you get your solution in the end, it'll be a complex number, and you can transform it back into the time domain representation, which is something, a cosine function of some sort. So let's do an example of how this goes about. So I look at the circuit here. Let me get my pen going. Whoops. Sometimes the pen is touchy. Let's do this color, that's fine. Blue. Yes, okay. So here's the circuit that we're going to look at, and I have capacitance values, I have an inductance value, and I have a frequency here, or a sinusoidal source, which happens to be a current source, so that's in amps. So I can see just by looking at that omega is 2, and it's what units? They don't do units very well in this book. Radians per second. That's the angular frequency of that the circuit is running at, and of course we know that omega equals 2 pi f, so we can find out what the frequency is in hertz if we want. And so this is an amplitude of 10 and an angle of 0 degrees, because there's no phase term here after the 2t. So in complex number space, that's just 10 plus j 0. So I want everything to be expressed in complex numbers on this circuit. This is 2 plus j 0. This one right here is a little bit, you have to do a little bit more, so I find out what basically the resistance of this capacitor at the particular frequency that we're operating at. We need ohms. We need everything to be in ohms. So 1 over j omega C, which is minus j over omega is 2 and C is 0.2, so that ends up being minus j 2.5 ohms. And then similarly down here for XL, so this is minus j 2.5, and XL equals j omega L, which is j 2 times 2, which is j 4 ohms. and this is still 4 ohms, and this is a dependent voltage source, 3Vx, depends on this voltage that's right here, but what is that voltage right there? It's actually 3V1. So, because Vx is the same as V1. So you go through and you take the circuit and you just replace all of the components with their imaginary or real numbers so that everything is expressed in ohms in this circuit. And then after that we solve the circuit using techniques that we already know. And we're supposed to use nodal analysis at this circuit. So nodal analysis is using Kirchhoff's current law applied at two different or applied at the nodes in the circuit. I have node 1 and node 2. So at node V1, apply KCL. So I have current going in right here, current going out right there, current going out right there. So but at node 2, current will be going in, and I will make current going out that way, and I will define current going out that way. And if I get a negative answer, I know it really goes the other direction. So I have two nodes. So at node V1, current in is 10. It's 10 plus J0 equals currents going out. Current going out is going to be V1 over 2 ohms. That's this current plus V1 minus V2 over minus J2.5, because that's the ohms right here, right? J2.5. So it's Kirchhoff's current law applied to node V1 because we're doing nodal analysis. And so I rearrange the terms a little bit here. 0.5 V1 plus complex number or imaginary number in the denominator, that actually becomes J 0.4 in the numerator, V1 minus V2, and in the end I get 10 equals 0.5, so V1 plus J 0.4 V1 minus J 0.4 V2. So this is one equation. So you do the same thing at node V2, subject to this extra condition here. So anyway, so we do the same thing at node V2. I have current going in equals current going out. So V1 minus V2 over minus J2.5 equals current going out. That's current going in equals current going out. So it's V2 over that inductor, J4, plus, and this one is V2 minus 3Vx, V2 minus 3Vx divided by 4 ohms. And of course we know that Vx actually equals V1. And so then you do the math and get the like terms together, and you will end up getting V1 0.75, yeah, plus J 0.4 plus V2. I don't have everything together. So I have minus 0.25 minus J 0.4 plus J 0.5. Okay, I got to simplify that. Equals 0. So I'll simplify that. So in the end, you have one equation here and a second equation here, and so I have two equations, two unknowns, V1, V2. It's the only thing is that these numbers are now complex. The coefficients are now complex. So we can go ahead and solve that. I solved it in MATLAB. I actually wrote out the matrices. I made this into a matrix equation because that's how it works well in MATLAB. So in MATLAB, I said my coefficient matrix is this. This is the first row. This is the second row. There it is written out. So it is literally, this is the A matrix, V1, V2 equals 10, 0. So this is the matrix equation describing our two equations and two unknowns. So this is just how you put it into MATLAB. That's the syntax for putting a matrix into MATLAB. B has to have this little symbol for being transposed, so that B, because B equals this, right? So it's in that direction. It's a column vector. It's called a column vector. And then to solve for V1, V2, V1, V2 equals inverse of this A matrix times the B matrix. So then you can get the solution. You can also do it with determinants. You can also do it on your calculator. There are many ways to do it. I actually show you MATLAB because I know Manoa uses MATLAB. And so anyway, I solve for inverse A times B, and I get V1, V2 equals these two complex numbers. But that's not how we want to express our solution. We want to express our solution back in the time domain. So you have to find a magnitude and a phase. So I did it first in MATLAB. Absolute value of V1, that's absolute value of V1. And it equals 11.327. If you were to do it manually, this is the formula that you need to do. Square the real part, square the imaginary part, take the square root of, and you'll get magnitude. To find a phase, I used MATLAB, their angle function right here, angle of that, and then I converted it into degrees. But you could also say tangent to the -1 of the imaginary part over the real part, and you get the same answer. So I showed you the details for V1. There's the magnitude right there, and the phase calculated out to be 60 degrees. There's the phase, and we knew that omega was 2 radians per second, and then that's our final solution. And the same thing, you take the V2 complex number, find its magnitude and phase, and put it back into our time domain solution. So it's really solving the problem with methods you already know, except that now all the numbers are complex. Next example doing nodal analysis in your textbook is one that involved having to recognize that you needed a supernode. The techniques are still the same as what we did in Chapter 3. I actually clipped out a part of Chapter 3 right here to refresh your memory, and I decided I'd go ahead and show it because this is a good review of some of the analysis techniques that we learned earlier in the semester, because they'll show up again, of course, on your final exam. So here's the circuit, and in this circuit they didn't give you this time the frequency that it's running at. They said, okay, there is some frequency, there is some capacitance, and when you compute the reactance, XC, reactance will be minus 3J ohms. Similarly for this inductor, its reactance will be J6 ohms, and then you have this voltage source over here that has a phase angle of 45 degrees with respect to what the phase of this current source is. But both of these things are running at the same frequency. We don't actually know what the frequency is in this circuit, but they're both running at the same frequency. But there is a phase difference, as typically in these kind of circuits, current and voltage are not in phase with each other. So the thing that you have to recognize here is you have two main nodes, and you have a voltage source that's between those two main nodes. So that causes us to create a supernode right here. So again, I've reclipped things from Chapter 3 to remind you what happens, what the process is for recognizing and creating the supernode. So let's do this problem. So the first thing you want to do is recognize that there's the supernode right here. So it's one node, and then you do KCL at that one node. So I have the current going in equals the current going out through this leg, which is V1 divided by minus J3. Then the current going out this node, V2 divided by J6 right there. And then the current going out, still this node, which is V2. It's just one big node really, but this is V2 here divided by 12. So I did KCL right there. Fixing that up a little bit, you get this math. And then, so we have a V1 and a V2. We need a constraint equation. And what we recognize here is that V1, this voltage right here, equals this voltage here, V2, plus this 10 volts at a phase angle. So that's what we write right here. I clipped some of these out of your textbook because the V's are bold to remind us that they're really vector-like quantities. So book wrote it here in vector-like quantity. I went ahead and converted it into the complex numbers because to me you're ending up doing everything in complex numbers. And so then I just go through some ugly math here, combine this equation and this equation together into one. You get this ugly complex equation. Simplify it down, I get V2 equals that, and then I can put it back into magnitude and phase notation, and I'll get this voltage. Then I go back and say, oh, I have V2 now. Let's find V1 back from this original equation, do a bunch of the complex math, and you get this final answer. So moving ahead, now we can apply mesh analysis to a circuit just like we did before in Chapter 3. Only again, we're going to replace all of the components with their various frequency-dependent resistances, or in other words, reactance. So replace all the capacitors with this reactance, to find out the reactance for each of the inductors, and resistor is still a resistor. Little reminder there that this only applies to planar circuits. So I guess we'll go ahead and do one example of a mesh analysis. In this next slide here, we'll do our one example of a mesh. So you want to write loop equations around each one of these loops, loops 1, 2, and 3. So around loop 1, you have just putting these complex numbers or imaginary numbers, AI1, and then this is going to be J10I1 minus J10I3, and then this will be I1 times minus J2 minus the I2 component. So writing that all out here, we get this first loop equation. We do the same thing for loop number 2. Please note that 20 at an angle of 90 degrees is really J20. So put it in the complex notation here so that you can deal with the math. And then for loop 3, we already know it's 5 amps at an angle of 0, so you can just substitute that back into the equation from loop 1 and loop 2, and you get these two equations in the end with the unknowns I1 and I2. Again, everything is complex numbers, but now we can go solve these two equations and two unknowns by any of our normal means that we have at our disposal, which is one, either a substitution method, solve for I1, substitute it back into I2, or a Kramer's rule using determinants method, or a matrix method. So 3 different ways to solve simultaneous equations. You don't need to watch me do all of the math here, so we'll continue on. So superpositioning applies again here. There is one little catch, that the superpositioning certainly applies if you have one frequency in a circuit, but it also applies because we have linear circuits that you have different frequencies in the circuit. So you can analyze the circuit all at one frequency, and all of the reactances and impedances will depend on that particular frequency, but then you have to analyze it a second time with the new frequency, because all of the reactances and impedances will change again. And so then you can get the total response by adding the two individual responses, but you have to add it up in the time domain. So you cannot add them up in the frequency domain. Why? He says, right? It says why right here, because the e to the j omega t is implied in our sinusoidal analysis, not explicitly written. So we have to go back and write things in the time domain before we can add cosine omega 1t to cosine omega 2t, because this part doesn't, the omegas don't explicitly appear in our phasor analysis. So I don't need to do a superpositioning example. It's just the same thing that we've done before, but all with complex numbers. Source transformations also apply, only now instead of having a source and a resistance like we had before, we now have a source that possibly has a phase relationship to it, and then we maybe have a complex impedance here. Impedance is Z. So these two transform back and forth. I will do an example on this. One of the things this chapter didn't really emphasize was that you could, after you replaced every component with its phasor notation, in other words, replaced all the C's with minus J something, and replaced all the L's with J something, that you can do all of the circuit simplification techniques that we also learned. So series, parallel, everything still applies here. And the book didn't really, this chapter didn't really mention that for some reason. So we'll go ahead and do an example so that will emphasize that. Well, there's certainly more than one way to do this problem. Just like a lot of circuit problems, there's certainly more than one way. I would first convert this out of this magnitude and phase notation. And what is that? Well, this is minus 90 is a minus J, so that's minus 20J plus 0. Of course, the real part is 0. So it says they want to use methods of source transformation, so the only transformation that I can see right now is converting this into a current source parallel to a resistor. So I'm going to do that first. Convert source using our source transformation things. So the current will be voltage divided by resistance in this case, which is minus 20J divided by 5 ohms. So that equals minus 4J amps. And so now our circuit looks like this. J4, I should say, not 4J. But and then I have a 5 ohm. And this next leg right here, I can just combine the 3 ohm and the 4J. So I'm just going to make that a block, an impedance block right here. And that's a 3 plus J4 right there. And then that's in series with a 4. Or I could actually impedance block it too, so why don't I do that, make it an impedance block. So that component right there is 4 minus J13, and then I have the component that I'm interested right there, which is 4. So now my circuit looks like that. I don't really want to some things that I could do is I could do some combinations and compress this all down to one big Z, but that doesn't really help me a whole lot because I really want to be able to get the voltage here. So if I get the current here, I get the voltage here. So I'm going to now, in the next step, combine this parallel combination into one component. So I will then have a minus J4 minus J4 current right here, and I'm going to combine down to one impedance block right there. And then over here I actually can combine it into one impedance block here, add these two together, I get an 8 minus J13 over here. So I'll find this impedance block right here, so that one is found. So these two components are in parallel. What's the formula for doing things in parallel? For only two elements, you can say this times this divided by the sum of the two. So the Z for this block equals 5 times 3 plus J4 over 5 plus 3 plus J4. And then when I do that, I get 2.5 plus J 1.25 ohms. So now the last thing I can do is I can take these two parts and do a source transformation back the other way. So then I'm going to make a new source transformation like this with some Z that's right there. And then I go back over here and I have this, it's almost like it's the load part, although 4 ohms of it is the part that I'm interested in. This part, this leg right here. So I do that. So this V, I'll call it V new. So that V is I times R. So V new is minus J4 times, not R, but Z. So it's times 2.5 plus J 1.25. And then I do that math, and I will get 5 minus J 10 volts. So this is 5 minus J 10. So, and this Z is still the same Z. It's still 2.5 plus J 1.25. So at this point, I can certainly find the current in the circuit if I'd like. I could also use a voltage divider formula to get the voltage that's across here. If I'm going to do that, I think I'm going to break that back out to use a voltage divider formula. So let's do that. So this was a block right here, an impedance block 4 minus J13, and then we have this resistor that we're interested in, which is just a, oh, I messed up, that was a 10, so that would have been a 14 right here. So okay, and that's 10 ohms. Okay, so let's just use voltage divider formula. So V out, or Vx is 10 ohms divided by the total impedance, which is 2.5 plus J 1.25 plus 4 minus J 13 plus 10 times Vn, which is 5 minus J 10. So far so good. I think I come out here with the right answer. Yes. And in the end, you'll get some complex number as an answer, and then you'll take your complex number and you'll convert it back to a magnitude in phase, which I'm just going to take it from the textbook right here, but I walked you through the process. Volts. So what you see is that all of the rules, whether we're doing source transformation, whether we're combining parallel elements into a single element, all of the rules are still the same. The only thing that's changed is that I'm working with complex numbers now, and I can't really draw a single component here, so I draw them as impedance blocks. Z blocks, impedance, Z is impedance. So each one is an impedance in ohms. We can also do Thevenin and Norton equivalent circuits, which is sort of has some relationship to those source transformations. But recalling, if you have some complex circuit here and you have 2 terminals, you can convert this complex combination of circuit elements into one equivalent voltage and one equivalent impedance. And there is a Norton equivalent that relates to it by source transformations. So the rules to find a Thevenin's equivalent are exactly the same. The only additional effort arises from the need to manipulate the complex numbers. Op-amp circuits also are still operated, well, at least when they're operated in the linear regime. We can do the same type analysis as we did before for op-amp circuits, and we make the same assumptions that no current enters either one of its terminals, and the voltage across the input terminals is 0. So, no voltage difference between the 2 terminals. Those are the 2 most important things to keep in mind, and then analyzing an op-amp circuit is just like analyzing any other circuit, except most of the time in an op-amp circuit we want to know the ratio V out over V in, which is called the gain. Sometimes we also want to know other things like V out over I in and so forth. Those have different terms, transimpedance, things like that. But typically, at least for most applications, we want to know V out over V in. So that's the only additional step, is finding that ratio. So the examples that were given in your textbook, sometimes I think they're just complex for the sake of being complex. But this circuit is a practical circuit, and it has applications. Since we're looking at it in the sinusoidal steady state, which was kind of strange that they put a DC source right here, but they did. That's actually not correct. This probably should have been an AC source right here, because we are looking at things in the sinusoidal steady state, right? So this probably should have been an AC source right there. Typo in the book. But this circuit actually has a lot of applications depending on whether, depending on the component values here, the ratio of the feedback to the feedback impedance to the input impedance. Doesn't this just look like a inverting amplifier to you, for example, right? But now we have C's in there. Next semester when we study this circuit, we will study this circuit, how it behaves as the frequency varies, and that's where it becomes actually quite interesting. But even be able to set up the V out over V in, which is called the transfer function, is very important right now. So the first thing you do is find what the Z's or X's are. So the reactances, XC equals 1 over J omega C2, that's XC2, and this is XC1 equals 1 over J omega C1. So I see a C in parallel with an R, so I will just call that Z feedback. So two components in parallel, what do you do with it? You say R2 XC2 over R2 plus XC2, and then it's a matter of doing the algebra. R2 times 1 over J omega C2, R2 plus 1 over J omega C2. This is actually, when next semester when we look at this circuit more, this is actually not a nice form to leave this in. So we want to simplify that into a nicer form, and this is how we do it. I'm just going to multiply the numerator and denominator times J omega C2, and then I get R2 over J omega C2 R2 plus 1. This, we will find next semester, is a very useful way to have this form. So then we also have an equivalent Z here, and I like to draw my circuits this way. I like to put that's the Z in, that's the, I'll draw it the rest of the way here. That's Z feedback right here. So I kind of genericize, because ideally in reality we could have inductors and things in here too. So we are interested in just having a generic, knowing what the impedance Z is. So Z in is two components in series, so it's R1 plus 1 over J omega C1, and we simplify that a little bit into a form that is going to be useful to us, and we will actually find out by putting it over a common denominator, 1 plus J omega R1 C1 over J omega C1. And so the closed loop gain and phase shift for the circuit. So closed loop gain is basically our V out over V in. V out over V in is closed loop gain, and that's often given, not to be confused with susceptance, but that's given often the symbol G for gain. So the gain of this circuit, closed loop gain, which means the feedback is connected up, is just from recognizing that that's a inverting amplifier. Oh, shall we go through the whole derivation? Let's go through the whole derivation. Your textbook didn't do it, but let's do it, just for the fun of it. oops, there we go. Okay, so we obey the op-amp rules. So this is V in right here. This is 0 volts right here. And by our op-amp rules, this is also 0 volts. And this is V out over here. And of course, it's V out relative to a ground connection if I were to connect up my oscilloscope or multimeter there. So I'm going to say current going into the node equals current going out of the node. Draw my current going in, current going out right there. So I have V in minus 0 over Z in equals 0 minus V out over Z feedback. So then I want V out over V in. So V in over Z in equals minus V out over Z feed implies that V out over V in equals minus Z feedback over Z in. And so we derived for the op-amp what the gain is. It's this formula right here. We have Z feedback right here. We have Z in right here. That equals the gain. So the gain equals, when you plug it in, you have an ugly equation, minus J omega C1 R2 over, and then you have these two terms in the denominator, 1 plus J omega R1 C1, 1 plus J omega R2 C2. So that's what the gain is, and you have an omega right here, which is frequency, right? And so you could actually plot this, oops, I did it again, plot this function right here, gain as a function of omega, and figure out what the circuit does as the frequency is changed. And that's a lot of what we're going to be doing next semester. We can make filters, we can make all kinds of things by understanding what the frequency response of these circuits are. So the last thing to do is just plug in all the R's and C's and crunch the numbers, and you'll get an answer. And the textbook says that the gain is 0.43, so it's attenuated at an angle of 130 degrees. At that particular frequency it attenuated, but it may be that at other frequencies that there's a nice gain in this circuit. And that's excuse me, a lot of what we'll be studying next semester. So the last thing that I wanted to cover in this chapter is some simulations, but I'm going to make that a different video partly because Multisim is on a different computer for me, so I have to switch computers and make a different video over there. But some of you didn't turn in the RLC simulation, so I think that I need to spend a little bit more time on how to do both transient and steady state analysis in our simulation programs. So that's the next video. Okay, bye.